Hello students, welcome to the EN 401 lecture on ship stability and weight. Ship stability and weight gives us a taste of the boats class, which lasts a semester, or the naval architecture major, which lasts several years. Why is studying this important? Largely having some basic knowledge can help alleviate some safety concerns, such as what you're going to see when you watch these two videos below. So I recommend pausing this recording and going and watching, clicking on both of those links. I'll give you a second to do that. Okay, the link on the bottom left is a C-2 Greyhound taking off from an aircraft carrier with a cat shot or a catapult shot. If you've ever taken a cat shot before, you know that there's an extremely high acceleration forward from the steam catapult, pushing you forward as you're lifting off, getting to a airspeed at which the plane can sustain flight when it reaches the bow of the ship. Part of that acceleration often or would cause a shift in the contents of the plane aft if they weren't strapped down properly. So in this case, that's exactly what happened. The C-2 Greyhound is a cargo plane. The cargo shifted aft due to the high G acceleration forward, and with that aft shift, the wings stalled, they lost lift, and the aircraft pitched up so much that it exceeded the ability of the pilots to correct that pitch with the flight control inputs, and they fell to the ocean. The helicopter on the right was not a longitudinal center of gravity shift like the Greyhound, but the H-60 on the right was a transverse center of gravity shift, and that appeared to be largely due to the ship that it was on turning. So as the ship turned, it caused the helicopter to roll to one side, and once the center of gravity of the helicopter rolled outside the main mount or the wheel of the helicopter, then it caused an overturning moment for the helicopter. Normally the center of gravity of the helicopter is right between the wheels, which keeps it stable on deck, but in this case the center of gravity of the helicopter went beyond the wheels and it crashed. So previously we discussed Archimedes' principle, and we've also discussed the location of the center of gravity for a basic hull shape, as well as the center of buoyancy, K being the vertical center of gravity or center of buoyancy as it relates to the keel. So both of those are always either 0 if it's at the keel or positive numbers if it's above the keel. Transverse center of gravity and buoyancy is left and right of the center line of the ship, or port and starboard, and then longitudinal is fore and aft. So what happens when one of these centers, what happens to these centers when a weight is shifted, when it's added or removed? So that's what we're going to talk about today. And then how does shifting a center of gravity, for example, of a ship, affect the stability of the ship? You might be able to guess adding a weight to a ship will cause the center of gravity of the overall ship to shift in a straight line towards where the weight was added. So if you add a weight at the top of a ship, the center of gravity will shift up towards that weight. If you add a weight at the bottom, it will shift down. Conversely, for a weight removal, the center of gravity will shift in a straight line away from where the weight was removed. And for a weight shift, so if you move a weight from one spot on a ship to another spot on a ship, the center of gravity of the ship is going to move in a straight line parallel to the direction the weight has shifted. To be safe, you can treat a weight shift as a weight removal and then a weight addition, and you'll get the correct answer. So here's a picture of a box-shaped ship in equilibrium. We're looking at the bow of the ship, and you can see the center of gravity is marked by a gray X in the middle of the ship. The center of buoyancy marked by a blue X below that, which the center of buoyancy is located in the center of the submerged volume, so it's the center of the rectangle that's submerged. And then in the upper right you see a orange weight which is added to the ship. So what's going to happen to the center of gravity of the ship when you add that weight? well, it's going to shift in a straight line towards the weight that was added. So you can see the original center of gravity location, and then you can see up and to the right of that a little bit is the new center of gravity location of the overall ship now that you've added the weight. And then this slide shows what happens to the ship as it re-achieves static equilibrium. So you've got the new center of gravity of the ship, and the center of buoyancy of the ship originally was on the center line, but now it's shifted to the right to correspond with the new centroid of the submerged volume. And anytime a ship's in equilibrium, the center of gravity and the center of buoyancy are in a vertical straight line with each other. So as the center of gravity shifted to the right, the center of buoyancy also shifted to the right to regain static equilibrium. This slide shows that the stability of a ship also depends on the list angle of the ship. So on the top left, number one picture, you see that a small shift of the center of gravity to the right causes a small list angle. The second picture, the one on the upper right, you see a larger shift of the center of gravity, and you see the center of buoyancy has shifted further to the right. So we've got now a larger list angle. If the ship were to continue to list, as in the bottom left, you can see that the center of buoyancy has actually reached the max ability of it to shift right to match the center of gravity. And so now the center of gravity is actually more to the right than the center of buoyancy. And so you have what's called an overturning moment. And so the ship, once it reaches that list angle, is actually going to continue to list further and further. It's no longer stable, and it's no longer going to return upright. And so then bottom right, number 4, you see that it's actually flipped on its side. That's if you're lucky. A lot of times it'll flip upside down and completely capsize. So what makes a ship more stable or more likely to be able to right itself if it's perturbed a certain list angle? Well, it has to do with what's called the righting moment. And so these drawings here show what the righting moment is. So what causes a ship to list? Well, sometimes it could be the wind. Most of the time it's probably a turn as the rudder is activated, then a ship will start to heel one direction or the other. But in any event, a large part of the stability of a ship has to do with where the vertical location of the center of gravity is. So the drawing on the left, you've got a high center of gravity in green. You've got a low center of gravity in black there. And then in both you have the center of buoyancy in blue. And so if wind were to push a ship over to a list angle like you've got on the right, then you can see that the high center of gravity, the green, is actually closer left-right to the blue arrow than the low center of gravity, the black one. And so what we have labeled there, D, is actually the distance from the low center of gravity to the center of buoyancy. And so that D value would be larger than it would be if we drew it from the green arrow. And so the righting moment for a ship, as it says below, is the left-right distance between the center of gravity and center of buoyancy times the buoyant force. And so wherever you have a lower center of gravity, you're going to have a larger righting moment, and a higher center of gravity, you'd have a lower righting moment, making the ship less stable. This slide shows the vertical weight shift equation that we use anytime we're trying to calculate how much the center of gravity of the ship is going to change in the vertical direction when we either add a weight, subtract a weight, or shift a weight in the vertical direction. So it's important to know what each of the terms mean, and so I'll quickly go over those. The term on the left, the capital KG new, that's often what you're trying to find, which is the new vertical center of gravity of the ship after the weight addition or removal or shift. The first term in the numerator, the KG old, that's the vertical center of gravity of the ship before you added, subtracted, or shifted the weight. That delta S old, that's the old ship displacement, so that's the weight of the ship before you added, subtracted, or shifted the weight. The next term there, that's the sum of any of the weights that you added, subtracted, or shifted times the KGI value, or the vertical center of gravity of that weight itself. And then the denominator is, again, the old ship displacement plus the weights that you add, subtract, or shift. And so the WI term is always positive if you're adding weight. It's negative if you're removing a weight. And if you're shifting a weight, then the best way to do it is to subtract the weight, is to treat it as a weight removal and a weight addition. So first remove the weight from its original location and then add the weight back in to its new location. This slide shows the table method that you may want to use as you're trying to solve these problems as a way of organizing your work. So the column on the left shows the object itself. So for all these problems, you're going to have some original ship, and then you may have a weight that you're adding, a weight you're removing, or you could have a weight that you're shifting as well. In this table, we just have three objects. We have the original object, the ship, and then we're going to add a weight and remove another weight. So the next column shows is the KGI value. So that's just where's the vertical center of gravity of the ship above its keel, and where's the vertical center of gravity of the weight that you're adding above the keel or the weight you're removing above the keel. KGI is always going to be a positive number, or it could be 0 if the weight you add or remove is actually at the keel itself. The next column, the WI column, that's just what is the weight. For the ship itself, it's actually that delta S sub-zero term, so it's the original weight of the ship. And then if you're adding a weight, it's a positive number. If you're removing a weight, it's a negative number. And then the next column is just the first two columns multiplied together, KGI times WI. You end up taking the sum of both the WI column and the KGI times WI column. And then if you look at the KG new equation, which is written there at the bottom, you see that the KG new is actually, the numerator of that is KGI times WI, the sum of that column, and then the denominator there is the WI column summation. And then you can do the same thing. It's almost the same equation and almost the same table for a transverse center of gravity shift. The only thing that's different to keep in mind is that the ship's center line is considered 0, whereas any shift that originates from the starboard side is positive, and anything from the port side is negative.